Wow, that was loud. I'm gonna have to hit the volume on that. All right, so yeah, that's not gonna work. So can you do me one more favor, Tanner? Can you turn out both grays and leave the reds? I think that works. Better? All right, so you guys who rely on that one, hopefully that works out okay. You guys rely on this one, well, it's no problem over here. So let me just do that. There we go. All right, so let's get started. Today we're going to talk about work and energy, but more important, today we're going to really talk about what the problems are going to be like, what I'm going to ask of you, and what a lot of this means. So we are talking about energy today, but most importantly, we're talking about work problems, or problems that involve the concept of work. So there, this is my my setup. I have a box on the ground. We're going to try and move that box by applying a force and sliding it 10 meters across the floor. And I want to talk to you a lot about the definitions surrounding the concept of work and what it means to talk about work and energy. And what I realized is that I have not really taken a moment and talked about what energy is. We talked about what work is, and we covered the different types of units for energy and what energy was like with chemistry. But as a broad concept, talking about energy is difficult because you have your own definitions for energy already. And in addition to that, one of the things that I've often found with students is that your colloquial definitions don't line up enough with our definitions for them to be useful to you. And so you often have these misconceptions about what different topics are about. So let me be very clear, and here's what I want you to have available in your notes. There are 3 things about energy that you should know. Energy is A, motion at its most basic level. It's temperature. That's from chemistry. Things that were hotter had more energy. But in our class, because we're dealing with the physicalness of our environment, energy also represents the capability of doing work. The problem is that throws down the word work. So let me say that definition again. And if I'm talking too fast, energy is temperature, motion, and the capability of doing work. Another way of saying that is the capability of changing something else's energy. That's really what having energy is about. Your ability to give that energy to something else. Your ability to do something with the energy you have. That should fit your definition of what it means to have energy. When you describe yourselves as having energy, you tend to feel like you can do things. And when you describe yourself as being out of energy, you tend to describe yourself as being tired and unable to do things. Like a couple of you every morning. So when we talk about the idea of energy, it's not too far away from your ideas that you've had growing up when your parents say, well, you have a lot of energy today. But for us, there is a physicalness to it. There's something that is measurable, something that can be quantified, and that part's important. And I also need to remind you about the word work. Work is how you change an object's energy. So when we talk about work, we're talking about doing something to another object, giving it energy or taking that energy away. And I want to be very over the top here. When you do positive work on an object, you give that object energy. Now, that very likely means that object did negative work on you. It took away your energy. So keep in mind that doing positive work increases something's energy, but negative work takes your energy away. Work is by how much your energy changes. Now, I want to set up a problem, one that's relatively straightforward. And let's start with this. We're going to have a 20 Newton force acting on a box at an angle of 30 degrees. And that box has a mass of 5 kilograms. It will be slid across the floor a distance of 10 meters. And let's go one step further and state that the ground has a coefficient of kinetic friction of 0.25. This is going to be our setup, our problem that we're going to use to kind of talk about how work is calculated. And I'm going to be a little over the top here, but I want to do something I haven't really done so far this year, and I think it's causing some trouble for some of you. I want to approach this from the standpoint of telling you exactly the style of questions that are going to be asked on tests, as opposed to trying to help you get a broader concept and see if you can use your creativity to apply it. That hasn't always worked out for some of you. So I want to be very particular. There are two specific types of work questions. Two, very specific. And they are deceptively similar, but they have a very big difference in what's being asked. The first, and what we're going to talk about first, is a category where it asks for the work done by a particular force. The first type of question that you'll be asked is to find the work done by a particular force. Now, here's where I do something I don't normally do. I'm going to give you the three different examples of what that will sound like on a test. For example, it could be that they'll ask, what is the work done by the 20 Newton applied force? They're being very particular here. That's example number one. What is the work done by the 20 Newton applied force? Another example of this could be to ask you, what is the work done by the normal force? A third example could be to ask you, what is the work done by the frictional force? These questions all refer to a specific force, and therefore you're being asked to calculate the work done by a specific force. That's the first category of problem. The second category of problem is deceptively similar sounding, but is asking for something completely different. Because they could ask you for what is the net work done on the box? 2 words, net work. What is the net work done on the box? There's 2 ways they can ask this question too. They could ask for the net work done on the box, or they could ask for the work done by the net force on the box. These are the same question. So the word net work or work done by the net force, they mean the same thing. Now, take a quick minute and draw a free body diagram. All right, I'm going to hit people up for some questions here, so be prepared to answer. Let's start with, I don't know. Emma, tell me one of the forces acting on the box.
Its weight is 50 newtons.
All right, so I'm going to draw a downwards arrow, 50 newtons. Thank you very much. So let's see. Samantha, tell me another force acting on the box. Excellent. There's my 20 Newton applied force. Excellent. Thank you very much. So Roxy, give me another force acting on the box.
There would be the normal force, which should be equal to 50 newtons.
I don't know if it's equal to 50 newtons, but I'll definitely draw the normal force straight upwards, just like that. Thank you. And Adam, give me another force acting on the box.
The friction is 0.25 times the force.
True. How did I draw it?
This way.
All right, so I'm going to draw a frictional force to the left. Is that what this way means?
Yes.
Excellent. So I don't know what the normal force is. I'm not going to jump at the fact that it might be 50 because I don't think it is. The applied force is pulling somewhat upwards on the box. And because of that, I think it's reducing the normal force. I don't know for sure because I haven't analyzed the situation. We're going to talk about analyzing the situation in a minute. But this is a good solid free body diagram. There are 4 forces acting on the box. You could be asked for any one of the work done by any one of those forces. So I could ask for the work done by any of those forces. That's asking for the work done by a particular force. And that looks very straightforward. The work done by a particular force is a formula. So it's relatively straightforward. if you know how big the force is and you know how far the box has moved, you could probably figure out the work done by a particular force. So I gave 3 examples, if you'll remember just a minute ago. I said we could talk about the work done by the applied force, the work done by the normal force, and the work done by the frictional force. Let's do all 3 examples. They're not particularly hard. Let's start with A, the work done by the applied force. That is the easiest question to answer here. Because to calculate the work done by the applied force, all I need to know is how big that force is, 20 newtons. I need to know how far the box goes, 10 meters. And if you don't have this in your notes because it was 2 weeks ago and you have forgotten, this angle, you need to be very careful. This is the angle between the applied force. I'm sorry, let me say that different. This is the angle between the force you're working with and the displacement. I'm saying that because you're going to make a mistake later. So this way I can rub your nose in it. It's the angle between the force you're working with and the displacement. For this problem, it's cosine of 30 degrees. That is the angle between the applied force and the displacement of the box. Anyways, work all that out and get yourself an answer here real quick. That one's straightforward. I don't care what the number part is, but I know you guys tend to, and it'd be nice if you had it for what we're going to do later. So I do want you to remember that the unit here is Newton times meter. That is a joule. Not the one that you use in the bathroom, but the one that we have here in the classroom. And I hope you got a number right now, 173. Yeah, 200 times 0.866. If your calculator's not in degrees, you probably got it wrong. There it is. That's right. I know who you are. I can see it on your face. Stupid pre-calculus. Calculus. All right, that one's pretty straightforward, I hope. No worries there. Let's do question B. Question B was harder, maybe. I asked for the work done by the normal force. But we don't know the normal force. So in a problem like this, where you're asked to figure out the work done by a particular force, you may have to use Newton's laws to figure out the individual force. That might have to happen, but not in this case. This case is a bit of a trick question, and it's aimed at certain people in the room who aren't really paying attention. They're paying kind of attention, but aren't really focused. Their mind is elsewhere because it's physics and they hate this class. I won't call you out, but I know who you are now. It's really kind of funny here, though. It comes down to the mistake people are going to make. I'm asking for the work done by the normal force. What direction does the normal force push? And the box goes to the right based on the diagram. So when I look at force times displacement times the cosine of the angle, the 3 things I'm looking for is the size of that normal force, the displacement, which I have. This angle, though, isn't 30 degrees. You'll put that on the test. I guarantee it. I've seen it every year. On a multiple choice test, I will have an answer here that looks like what would happen if you put 30 degrees in. But that's not the angle. The angle is 90 degrees. Theta represents the angle between the force you're looking at and the displacement. Normal force is up, displacement's to the right. That's 90 degrees, which means the normal force does no work because the cosine of 90 degrees is 0. I don't need to know the normal force here. The normal force and the weight don't do work. And the reason is very straightforward. Get this in your notes, highlight it, or whatever you need to do to remember this. Forces only do work if they're in the direction of motion. So there's no work done by the normal force because it's not in the direction of motion. And question C, the work done by the frictional force. Now, there's no way around this. We don't know the size of the frictional force. We just don't. Not from. It's not given. That doesn't mean we can't find it, because we do have information we could use here that sounds a lot like the Newton's law problems. When asked to do the work done by an individual force, you may have to use Newton's laws. If you're not given that force directly, you might have to do the work. So I'm going to take a brief pause here and give you guys 2 minutes to figure out the frictional force, the size of it. Because to calculate the work, again, 3 things are necessary, and one of them is the size of that force. So you've got 2 minutes, and at the end of those 2 minutes, I'm going to call on somebody I hope has the answer. And you guys know that I'm going to probably definitely focus on people whose cameras are off and or people I think have been sleeping through this lesson. So get busy, please. 2 minutes, starting now. Do. All right, I put some instructions on there in case you don't know what to do. One minute down, 1 minute to go. Eyeballing those black boxes. All right, that should be more than enough time. Sebastian, what is the size of the frictional force?
I did not finish.
Well, you know I'm not going to let you loose, right?
Yeah, I know.
All right, so let's work it out. Did you find the size of the normal force?
I was a little bit confused on that part when you put it up.
Well, let's start from the beginning here. In the y direction, I have normal. I have weight. But there's a part of this force that's also in the y direction. So we need to figure out all of the pieces here. We know the weight's 50. So you need to tell me how much of that 20 Newton force is in the y direction.
Is it 17.3?
Oh, yeah, 2 choices, cosine or sine. You guessed wrong. So when I wrap a triangle around it, I'm looking for the one that points up. That's the opposite side. And since it's the opposite side, I'm going to use sine. So can you try again for me?
10.
Excellent. Yes, the component that's upwards is 10 newtons. So it looks like I have normal force plus 10 minus 50. And what should those sum to equal?
Is it just n minus 40?
Yeah, but what does that have to equal? What is the net force in the y direction?
40? Oh, wait. Zero?
It does. The net force in the y direction does equal 0. So that does suggest that the net force, the normal force, has to be equal to 40 newtons. Sebastian, I'm going to need a little more from you from now on, okay?
All right.
So normal force equals 40, so I don't want to spend a lot more time on this. Frictional force equals how many? 10 newtons, that's right. Because 0.25 times 40 is going to give us 10. So the frictional force is 10 newtons. That wasn't the important part. My assumption is that since we finished those two tests, that I can ask this of you. So if you can't, you understand you can't do part of the work that you're going to have in your next test. So if that was hard for you, you need to keep up. Our tests are always cumulative, always. So 10 Newton force, 10 meter displacement. What's the angle between the frictional force and the displacement? That's right. Don't get caught looking on this one. It's 180 degrees. The frictional force points to the left. The displacement is to the right. That's 180 degrees. Which means that, oh, by the way, what is the cosine of 180 degrees? -1. So that makes this -100 joules. All right. We've done our work here. I've shown you how to do the calculation for the work done by an individual force. Yes, sir? No. And I don't want to come to the point where that's always going to be true, because friction could be in the direction of motion. I can give you a simple example. Okay, what direction am I holding my, see, I gotta get everybody looking at, you guys at home can see my little picture here, right? So everybody,
Yeah.
what direction am I pushing on my phone? Everybody agree that it's up? Now, if I want my phone to go to the left, my left, actually, I have no idea what you guys are going to see here, but if I move my hand to the left, the phone went to the left, clearly, right? I don't know if it went to the left in the video, but it went to the left from where I'm looking. Now, that being said, did I push the phone to the left? I pushed up. What pushed the phone to the left? Friction pushed the phone to the left. So in that case, friction was in the direction of motion, so it did positive work. Does that make sense? So I can't give a blanket statement that friction will always be negative. It won't. But any force that's not in the direction of motion has the potential to be negative. So I don't want to make this harder than it is. If friction is trying to slow the object down, it's doing negative work. Any force that's trying to slow the object down is doing negative work. Simple as that. So if I would rather you have a bigger picture of it, because if something's being thrown at you and you go to catch it, you're going to do negative work on that object because you're going to stop it, right? So if a ball's coming at you, you go to grab the ball, you're going to push backwards from the direction it's moving. It's moving towards you, but you're going to push away from you. So you're going to do negative work on the ball to stop it. So any force that's against the direction of motion does negative work. Okay, big picture. I need to see the big picture here for just a minute. Positive work was helping to change the object's velocity in a positive way, increase its speed. Work is not just about moving objects, it's about changing their energy. Energy isn't about position, it's about velocity. So this 173 joules of work attempted to speed the box up and change its energy. While that was happening, friction was trying to slow the object down, reduce its energy. However, the net work done on the box was positive 73 joules. If I'm asked to calculate the net work, one way to do so is to calculate the work from all the forces and then add it up. I'll say that again, because remember, there's two categories of these problems. If I'm asked to calculate the net work, I can find the work from all the different forces and then add them up. That is the net work. The word net means to add. I increased the box energy by 73 joules. Yes, sir. Say that one more time. The question in the classroom was, if I asked you for the work done by the net force, would this be the answer? And that's yes. Now, at the same time, I want you to pay attention to something else that's going on here. The net force on the box, when we talk about work, is the net force in the X direction, because that's the direction the box moved. So consider that there are two forces acting on the box in the X direction. There's 20 cosine 30 degrees. That's the amount of forces to the right. We saw that just a moment ago when we were talking with Sebastian. He told us that this was 17.3 newtons. And we also found that the frictional force was 10 newtons. So the net force on the box was 17.3 newtons to the right and 10 newtons to the left. Net force requires that we add up all the forces and take into account the direction of motion. That's what we've done here, which gives me a net force of 7.3 newtons. That was the net force on the box. You can calculate work done by the net force by just substituting in the net force. The difference is the net force will always be in the direction of motion. So that'll always be an angle of 0 degrees. And when I'm done, I'll have the same answer, 7.3 newtons times 10 meters times the cosine of 0 degrees. So 73 joules. You have two different ways of calculating net work. You can either figure out the individual amounts of work and add them up, or you can figure out the net force and use it for the work formula. However, this is a big however, this is the second most important thing I'm going to say today. There is something called the work energy theorem. And it is probably the most important thing that deals with work, because it's really about how energy flows through a system. And it says that the net work done is equal to the change in kinetic energy of your object. It states that the net work done is equal to the change in kinetic energy of your object. Now, I don't do this kind of stuff often in AP Physics 1 because I feel like it's sometimes a waste of time. But there are people in the room who are pretty smart and pretty mathy. And I like to do things with mathy students from time to time. If that's not you, if you can't describe yourself as being pretty mathy, you can check out for a few seconds and then just pay attention to the end. But if you're a pretty mathematical person, you might find this interesting. So let's talk for a minute about Newton's second law. Newton's second law says the net force equals ma. If we were to multiply both sides of this by displacement, we'd get net force times d equals ma, but I'm not going to write this with a d. I'm going to write this in terms of a motion variable, delta x. So at the left side looks like what we just used on the other page, but delta x looks like what we used way back in the day when we were using motion equations. Is that okay for you guys? Because delta x means displacement, And the D that we have here also means displacement. I'm using D because it's on your formula sheet, but delta X is better. Now, the reason I'm putting this out there is if you think back for a moment to your motion equations, you have one out there that's V squared minus V naught squared equals 2A delta X. Look familiar? I could divide by 2, and that would give me A times delta X. Well, over here, I have A times delta X. So I'm going to substitute V squared over 2 minus V naught squared over 2. Now I'm going to distribute that M, if you don't mind. And when I do, I get 1/2 mv squared minus 1/2 m v naught squared. And I know that we used initial and final, so I'll use initial and final for you guys. This is where the definition of kinetic energy comes from. This derivation. Kinetic energy is defined as 1/2 mv squared. The right side of this is our definition of net work. I'm sorry, the left side of this is our definition of net work. The right side of this is the change in kinetic energy. This is the work energy theorem, and this is a proof of the theorem. What's important to diagnose here, and this is big, if you didn't listen to the whole derivation, you should have this written down now, because this is the work energy theorem. But there's also your understanding of it, your ability to explain it. And here's what you have to be able to understand. If the force is unbalanced, then the net work will change the velocity of the object. But if an object's moving at a constant velocity, you know the net work has to be 0. Even if it's moving, even if it's changing location, if the object's velocity is constant, then the net work has to be 0. What that means is if the object's velocity is constant, for every bit of work being done by one force, that work's being taken away by another force. So imagine we go back to the situation with the box for just a minute. If I pulled with a force that was small and the box moved at a constant velocity, then yeah, my force did positive work on the box. But that means that friction is taking that work away as I'm giving it to the box. When I stop pushing on the box will probably stop moving. Ultimately, what happened was I gave energy to the box gave that energy to the floor. When I'm done, the floor is probably hotter than it was before. So it's a fancy way of heating the floor is pushing a box around the floor. Because that's what friction does. It takes the energy away in this case, creating heat. So when we talk about the flow of energy, the work energy theorem tells us a way of kind of tracking where that energy is going. But it tells us something very specific. If you do positive work on an object, then the object's velocity will increase. If the net work is negative, then the object's velocity will decrease. That's what the work energy theorem tells us. Now, we're reaching the end of class today, so I want to talk about the last piece of this. And it's how to know when to use what. We have three things here. We have the definition of work done by an individual force. We have the definition of work done by the net force. And we have the work energy theorem. These are the three things we talked about today. How do you know when to use which one? It's relatively straightforward. If your problem has stuff about forces, you see coefficients, accelerations. Well, I'm sorry, not accelerations. If you see forces, coefficients, masses, and Newton's law information, you're doing one of these. But if the problem describes velocity, you're probably doing this. Meaning I can ask a question about the work done on an object without ever mentioning a force. Here's an example. Let's go back to our box. Let's say that in this case, I don't know anything about the forces acting on the box. All I know is that when the box moves from its position here to its position across the way, so when it makes it over to here, the box is moving at 5 meters per second. So I could say that an object experiences a force of 30 degrees and moves a distance of 10 meters. And after it moves those 10 meters, it's moving 5 meters per second. How much work is being done on the box? That question would never require you use this formula at all. Even though I tell you how far it moves, even though I tell you the angle of the applied force, I'm trying to distract you because you don't have to do any of this. You know how fast the box is moving before and after that force. So you would go work equals 1/2 5 times 5 squared minus 1/2 5 times 0 squared. In this problem, I'm telling you how to find the work by using the velocity, not any of the forces. And you understand that that's how they're going to get you on these questions, right? 5 squared is 25. 5 times 25 is 125. Half of 125 is what? 62.5? Is that right? It's got to be close. I'm pretty sure it's 62.5. So I see people who can't pay attention until they have the answer. So do you understand that these work problems, they can mix. They can give you a little bit of force information to try and make you think you're supposed to do force times displacement. But if they give you stuff about the velocity, man, that's so much easier to do it this way, isn't it? You saw all the work we had to do before for each individual force. This is much faster. You need to be aware that our problems are going to mix this kind of stuff up. You have to be prepared to use all three of these things and know when to use each one of them. In fact, the fact that I just told you how fast the box was going at the end means you could tell me things like what the net force on the box was. It went it had a change in energy of 62.5 joules. That has to equal the net force times the distance. The distance it went was 10 meters. So I gave you a way of figuring out what the net force was. The net force had to be 6.25 newtons. These are the kinds of things that you're going to have to be able to do in your test. All right, that's a lot for one day. That's a lot to take in. Your homework's going to have this kind of stuff in it. So we're going to end right here, unless you guys have some questions for me. Kind of expect that because you probably don't know what to ask yet. And remember, seems easy when Mr. Shelton's doing it sometimes. So your practice is going to be posted today. It's going to be due early next week, like Tuesday. It's going to be about 15 to 20 practice questions out of the book. So please get started on it now so that you don't leave it all for the last evening. We're going to add to this tomorrow. All right. So they're probably going to interrupt us any second for us to be able to say the pledge. You know, my favorite part of the day. But are there any questions at home? Okay, you guys at home, you are free to go. Unless you want to know what's going to be on the bar today. I bet the hot bar is going to be the potato bar. 3 days running. I'm hoping potato bar 3 days in a row. Do they have mashed potatoes on the potato bar? You guys are so in love with mashed potatoes. Thought maybe.
Have a good day.
Oh, we will. So, all right. Well, you guys have a nice day then at home. I'll be here in case you guys want to say the pledge. You guys here in class? Class is done. Tanner, can you turn the lights on for me again now? I'm starting to get scared. Roxy's still here. She's waiting for our knowledge about what the lunch schedule is going to be today.
Yeah, I want to see if it's the potato bar.
I know, me too. I'm getting a little concerned because it's always the potato bar, and I just think
Yeah.
they must have got a good deal on potatoes.
I mean, it makes me wonder what's in the potatoes.
Ooh, that's creepy.
Yeah.
I wonder do they ever have sweet potatoes on the potato bar? Maybe let's downshift and get yams, but tell us they're sweet potatoes. We know better. Yams are not sweet potatoes. I don't know what the difference between a yam and a sweet potato is, but I'm sure somebody does.
Do they taste it?
They do taste different, actually.
I've never had them both and compared.
Well, I guess we're going to have to educate everybody. We'll have to get a group of root vegetables out and try all of them so we can see the differences between our root vegetable tastes. You know, potatoes, red potatoes, yellow potatoes, Idaho potatoes, sweet potatoes, yams. What else is there? What am I missing? I mean, there's other root vegetables like carrots, but I don't think they're the same thing. Parsnips, turnips. Is an onion a root vegetable?
I think so.
It looks like it should be a root vegetable. I mean, it's in the ground.
Yeah.
I've grown them before.
I've had a purple yam.
A purple yam? All right. How about beets? Beets have got to be root vegetables because they taste like earth. They're terrible things. Has anybody ever?
Like beets?
I do not like beets. I think beets is just punishment. People
Yeah,
in my home.
I
Are
grew
you?
up with a dietitian as a mother, so kind of had to learn to love beets.
Yeah, I hear they're a miracle food. Wow, you could just mix them up with a little kale and have just a lunch nightmare.
Yep.
It's good for you, but no, thank you. Yes, it is. Kale is decoration. It shouldn't be food. It's what they put around the salad bar so that you can know where the good stuff is and you avoid the kale. I know it's really popular now, but there was a time when that's all it was the stuff that you put around the salad bar, not the stuff you put in you.
Mostly, but it's really good.
I
We toast it. Like if you put it in little pieces and you toast it with olive oil and salt.
I can be convinced that kale is good in the same way I can be convinced that Brussels sprouts are worth eating. But we all know the truth, that it's all just putting lipstick on a pig. We're just trying to find a way to stomach that garbage because we know it's good for us and we've been told that we should eat it. I know. I'm just my opinion. I might be wrong. I'm talking to a person who's the daughter of a dietitian right now, so I'm sure that I'm wrong. So
Oh, no,
Roxy,
no, I totally agree.
excellent there. So we're all right here. How many of you, if given a choice, would say, oh, please, an extra helping of Brussels sprouts and kale?
Absolutely not.
What? It doesn't matter what the other option is. I'd be like, I ate my serving. I'm done. Push away. But would you really go, I'm still hungry? Yeah, I guess since the garbage is all that's left, put it on my plate. No, you wouldn't do that. I don't think so. Well, I could be wrong. I could be wrong. Well, I'm afraid that they're not going to do it. So let's say the pledge real quick. Ready? I pledge allegiance to the flag of the United States of America and to the republic for which stands one nation under God, indivisible. Amen. Have a nice day. We didn't even get the lunchman. Very disappointed. Thank you for hanging out with us, Roxy. It was nice to talk to you.
Nice talking to you too.
Bye, class.